probably one of the most important trends that comes up and is used in explanation again and again and again as we go through this course. So I'm going to move to the slide that starts electronegativity. And of course, as mentioned, this is our last trend, and the trend is for electronegativity. And if you need to or want to write down a definition for electronegativity, you will notice that electronegativity is an assigned number. It is a number, but it's worth pointing out it does not have a unit. This number is an indication, or it indicates the ability of an atom to gain an electron, and this is really important, during bonding. So each atom, or each type of element, an atom, it was analyzed by Pauli. We use the Pauli electronegativity table, and this value was determined by looking at atomic size, which of course relates to number of protons and number of energy levels, electronegativity values, ionization energy values, stability of the cations and anions, which we just talked about, and another topic which we haven't brought up, which is electron affinity, and it is not taught in general chemistry. So back to what this means, it's just a number, and it tells you how much the atom wants to gain an electron during bonding. There are lots of electronegativity tables around and found in most chemistry books. Often it's literally numbers plastered right on the periodic table. So let's take a look. We need to look at the electronegativity values of the noble gases. So we know that the noble gases are considered stable. So my first question is, are noble gas elements stable? And the answer is yes. There's a whole lot of math and theory as to why, but we have to agree they're stable. Do all noble gas elements have filled energy levels? And that answer is yes. That's why they are all grouped together. They have a filled valence energy level. That makes them stable. Next question. Do noble gas elements tend to lose or gain electrons? The answer is neither. They don't lose, they don't gain, they stay as they are. Because they stay unchanged, we might say they stay neutral. We might say that they keep their configuration. They don't lose, they don't gain. Another real good question to answer is, do noble gas elements commonly react? No. They usually are unreactive. That's what makes them stable. They sit there as atoms, they don't do anything. And last but not least, this is a summary of that means, so this means that noble gas elements have zero or extremely low electronegativity values. So if you go to that last column and you find helium and you find neon and you find argon and you find krypton and so on, you will, if you looked at a table of electronegativity values, it pretty much means they're zero or really extremely low. I am now going to forward the slide. In your high school book and in most books, you are then going to see that the electronegativity value for these elements is zero. This is important to point out. Now hold on, Miss Scott. The one at the bottom has an electronegativity value. Yes, it does. That is unique. We rarely look at that, but I also don't want to withhold information that's true. So for the most part, we still consider these elements very stable and unreactive. You might think I get this, but I want you to make sure that you write some of this down, because there will be questions where you have the option of picking one of the noble gases as something that has a high electronegativity value or a lower electronegativity value, and you really need to get used to the idea that they do not have an electronegativity value. And the reason they do not have an electronegativity value is because they do not react. And electronegativity value is the ability to gain an electron during bonding. They do not gain. Okay. Remember, you can pause at any point and re-listen to something, or take your time to write it in your own words so it makes sense. Okay, the reason we look at that is because now we understand we're going to be looking at the trend for electronegativity. We're going to look at the period trend, which means going across the periodic table from left to right, which is why this arrow is above the periodic table that I'm going to roll down to. When I roll it down, look at the numbers. You need to stay within a period. So I'm going to pick this period, or period 2. We see an electronegativity of 1 for lithium. We see an electronegativity value of 1.6 for beryllium. We see an electronegativity value of 2.0 for boron, 2.5 for carbon, 3.0 for nitrogen, 3.5 for oxygen, 4.0 for fluorine, and notice here, the noble gas is 0. You will notice that same trend in general across. And what we're observing is that the electronegativity value increases going across from left to right. Make sure you're writing numbers, drawing pictures, doing whatever is necessary. You will also notice that we often just focus on the elements in the 1A, 2A, and then in the 3, 4, 5, 6, 7, 8A. We do that because the transition metals sometimes present some unusual values. They do tend to trend higher still as you go across here. Occasionally you see an outlier. There are reasons for there to be exceptions. Right now we are focused on the general trend. If someone in class wants to ask about the exceptions, I can explain them. But in general, going across, we get a greater and greater electronegativity, a greater and greater desire or pull for an electron. Next, we need to figure out why. This increase is due to each atom in the period having a greater ability to gain an electron than the previous one. If you really want to know a short answer, this is due to nuclear charge. So as we look at lithium, which has 3 protons, and then we compare it to fluorine, which has 9 protons, we see the size of the atom decrease, and therefore the pull for the electron increases. It's like opposite. So if I pull for electrons more and I end up making it smaller, I also have a greater ability to gain an electron. So fluorine has the greatest ability to gain an electron. Another reason this trend is true is because as you move across, element like fluorine, which used to have 7 valence electrons, very much is interested in terms of octet, 8 electrons, and stability, wants to have that noble gas configuration. Remember, we talked about getting to a noble gas configuration or a pseudo noble gas configuration, and that's why this pulls for that electron. So it's that ability of an atom to gain an electron during bonding, and it increases going across because greater nuclear charge pulls it in, pulls for the electrons more. A little messy, but hopefully you made sense of that. If not, back it up, rewind it. It's pretty important that you understand it. When we then switch to the trend for electronegativity from top to bottom, we will notice that it seems to go down. So I will move this so you can see the periodic table that I have posted here. You want to pick a group that's probably like a representative group. Hydrogen, remember, is not actually a metal, so we want to focus on here down when we talk about the alkali metals, or from here down if we talk about the alkaline earth metals. In either case, you can see the number go down. Are there going to be times when it doesn't change too much at the very end? Sure, but in general, the numbers go down. That means that as you go down through the group, that the electronegativity value, or the ability to gain an electron, is decreasing. So our group trend from top to bottom is that the electronegativity value decreases. We might want to wonder why. And so I'll go back. Actually, I'm going to pause. So one thing that's a really good thing to do is to sort of step back now and look at this whole chart. We know we see it going less down here. We know we see it more going up. There's one element that really sticks out on the electronegativity value tables. I will also like to tell you that you'll notice it's color-coded, and depending on what kind of chart I give you, the red in this case would signify something that has an extremely high electronegativity value. I'm going to move to the next thing and ask you to note that element, or the element, that has the highest electronegativity value. This needs to be written in your notes, and you might want to even visualize or circle on your own periodic table that fluorine is the element with the highest electronegativity value assigned, which is 4.0. We want to wonder why. We have to be careful. Remember, the noble gases don't have electronegativity value, especially something like neon. So, wondering why. So, why would fluorine have the highest electronegativity value? And that's because it has the highest nuclear charge, which is 9 protons, with the lowest amount of shielding. Here. And the halogen below fluorine has more shielding, so it has a slightly less ability to gain an electron. Oxygen, right before fluorine, has a lower electronegativity value. Why? Because it has one less proton. Remember, the protons pull in, and if you have too many layers or shielding or energy levels, it's not as easy for the electron to be pulled in because of that shielding. If I go back up here, back, you will notice that from here, everything decreases. So some students like to think it increases as I go up and to the right. That's a great thing to remember. If I go down, it decreases. If I go back this way, it decreases. So you need to make sense of that. You'll notice for the halogens, which is this column right here, 4.0, 3.0, 2.8, 2.7, 2.2, decreasing. And that is because it's this atom, astatine, does not want to gain the electron as much as the fluorine. If I failed, and I may have, in telling you why fluorine has the greatest not why fluorine has greatest electronegativity, but if I failed in explaining why the trend is lower as we go down, let's talk about that real quickly. So if my trend going down through the group is that we get lower electronegativity, then the question is why? And remember, electronegativity is the ability to gain an electron during bonding. It's the same reason everything changes down through a group. I'll write one word. You need to be comfortable using the word shielding when you are explaining things. So shielding. What does shielding mean? More energy levels. So I'm going to pick something that has a pretty high electronegativity value. I'm going to start with fluorine, 4.0. I'm going to go to chlorine, 3.0. I'm going to go to bromine. I'll look up, back, and it appears as if bromine's 2.8 and then iodine's 2.7. You have to step back and you have to think, okay, what makes these different? 9 protons for fluorine. Chlorine has 17 protons. This is fluorine. Chlorine has 17 protons. Bromine has 35 protons. And the iodine has 3 protons. The rings get old, but for some kids it's a good visual. First energy level, 2. Second energy level, 7. Really, really, really wants to gain the 1 to achieve the octet. Really, really pulls for that. The high nuclear charge, the low amount of shielding, makes it very high, 4.0 electronegativity. We could then do chlorine. Chlorine has 17 protons, 2 in the first, 8 in the second, 7 in the last. Same thing. Very much wants to gain 1 electron to get to the octet. Does it want to gain it as much as fluorine? No. Why? Because there's more shielding. More shielding changes the attraction for the electron. It lowers to 3.0. Don't know if I need to do bromine, but I'll do iodine. So we'll pull that down. And we know we have 53 protons. So we know that means 2 in the first energy level. We know that means 8 in the second energy level. We know that means 18 in the third energy level. We know that means 17 in the fourth energy level, and we know that means 7 in the valence. Very much wants to gain that 1 electron, but because of all that shielding, it isn't pulling as much for the electrons, so it's assigned a lower electronegativity value of 2.7. So to summarize, your trends all fit into each other. Going across, and that's known as the period trend, we know atomic size or radius decreases. Our reason? The nuclear charge pulls them tighter. We know that the ionization energy increases. It takes more and more energy to remove an electron. We know the electronegativity value increases. Because it's pulling in on the electrons more, because it's a smaller size, it is more likely to achieve or pull in an electron. That's the electronegativity. Here is the group trend. Here we know atomic size increases. We know now we're dealing with extra energy levels, more energy levels are shielding. That means the ionization energy decreases. We know that means the electronegativity value decreases. All of these, remember, are due to shielding more than anything else. And all of this is due to nuclear charge more than anything else. Obviously, along the way, we've covered some weird exceptions, and you'll notice I did not put cations or anions on this quick summary. I hope you learned from watching these videos. Thank you so much. I look forward to seeing your notes and watching you work together in class. Thank you.